conducting wire or something like that over a constant magnetic field, that induces a current. Remember the little Mamba braking system demo that I did where we had the cars come down and it went over the conducting thing and they had the two magnets on the bottom and they stopped right away? Well, that's because of the magnetic force that was applied to them because they created a current. Okay? So, a moving conducting rod creates a current which creates a force, all right, which opposes the motion. Okay? So, in other words, we can't have a perpetual motion machine. All right? And we're going to learn some new phrases today. Get this thing. It's called the electromotive force. Now I'm going to go ahead and put force in quotes because it's really not a force. It's a voltage. It's a voltage. And you'll see it in a book written like this. You might have seen it in your lab written like that. E. It's the same thing as V. Okay, so it still equals an IR and all that stuff. But there's a way that we can get it. Okay, so let's take a look. Let's say we've got a little configuration here, a little light bulb. All right, a little light bulb here, and wires here, and I've got a metal bar here, and I'm going to push it. I'm going to apply a force applied this way. Okay? I'm going to apply a force that way. And this is a conducting rod. Okay? This is a conducting rod. Now here's what happens. Oh, I forgot the big thing. It's in a uniform magnetic field. Okay? There's my uniform magnetic field. I've got an applied force going that way. It's a conducting rod. These are conducting wires that are going to this light bulb. So therefore, if I push it hard, if I got enough room, if I push it along this track, it will basically create an EMF that will light the light. It'll push a current through the wire. That's kind of cool. Okay? And it also kind of gets us to the way generators work also. So, in other words, when I push this thing, you're going, well, wait a minute. Ohm's law says this. V equals IR. Well, where the heck do I get the voltage to create an IR? Here's my resistance here. And you're telling me that I get a current going through here. Well, let's think for a second. Inside a magnetic field, okay, this is a conducting thing, so it's got free electrons, right? Okay, and it's inside a magnetic field. So the magnetic field's going in, okay, and I'm going to push that thing this way, so those electrons will now have a velocity going. Since it's going in, they now have velocity going this way. So which way does the force go? Up, right? For the protons. It'll push all the protons up here. Well, it doesn't really push the protons. But since the force goes up, where do the electrons collect? Down here at the bottom. Okay, so I get a bunch of electrons down here, a bunch of protons up here. Hey, I made myself a battery. Is essentially what we're doing. Okay? As long as it's moving. Because eventually what it does is, see, the magnetic force that we create is going to equal that applied force because we're going at a nice constant velocity. If I speed it up, if I push it harder, it'll create more current. It'll create more energy in there. If I slow it down, it'll create less. If I stop it, it won't create any. Okay? So, how do we get our EMF? Now, so that's what they were talking about in the book when they talked about electromotive force. I got one more little demo, and we'll go back to this again. This is for like Lenz law, actually. Okay, so once again, I have a copper wire, good conductor. I've got a nail, which is a pretty good conductor. It's aluminum. If you happen to notice, the resistivity of aluminum is much higher than it is for copper. It conducts okay, but not real good. Okay? But copper's a good conductor. Now, when I drop this nail, bang, wow, it goes down there, hits it pretty hard. Okay? I'm going to put 2 magnets on there. So I'm going to be changing. So this time, once again, instead of moving the conducting rod, I'm going to be moving the magnets over it. Okay? And what that does is it'll create a force that will oppose the motion. And it will slow it down. And so it takes it a while for it to pop out the other end. Okay? And it's kind of cool when you show this. And I'll leave it up here at the end of class if you want to come up and try. You kind of get mesmerized. You can be in your office watching it just float down there for hours at a time going, I wonder how that works. Oh, yeah, I'm supposed to know. But anyway, so there's kind of a demo of, but this time we had the magnetic field moving over the conducting thing. Same thing. You know, if I decided I'm going to start moving, I've got the, as a matter of fact, that's kind of the way that that Tesla coil or that Van de Graaff machine works, that puts the charge over in that big ball, and you put your hand on it and your hair stands straight up, stuff like that. It works that way because what it's doing is it's moving, well, it's actually peeling charge off the rubber belt that's going through there. But the Tesla coil works this way too, where it's moving, the magnets are actually moving. Generators work that way. That's why we get those big turbines that turn when the water hits it. Okay? You get the magnetic field moving, so it creates a current that, hey, we've got power. Okay? All right. So let me make sure I get this right here. The electric motive force then in this situation, and remember, it's the same thing. When you see this fancy E, or we say force because it's really not a force, it's a voltage. But that voltage pushes charge. So things that, so the formula for the electromotive force is this. E equals the velocity, however fast this thing is moving with a certain velocity. Velocity times the magnetic field times the length of the rod. And here's the length of the rod right here. Okay? Velocity times, that's a bad marker. We won't use that one anymore, sorry. All right. Okay. I'm going to kill myself on this thing. We'll put it over here. Okay. So there we go. Let's say we're looking at example 1 so that when I'm a big meanie and I assign the homework problems for this chapter. By the way, a lot of you took advantage of Friday, or Wednesday, and got a lot of the homework 5 done, so that was good. All right. Okay, so here we go. It says here, suppose a rod, here's our rod here, we've got this configuration, is moving at a speed of 5 meters per second. All right, so then V equals 5 meters per second. Okay, so V equals 5 meters per second. And we've got a magnetic field. B equals 0.8 Teslas. And the length of the rod is 1.6 meters. Okay. What else do they say? The light bulb has this light bulb has a resistance of 96 ohms. Okay, so the light bulb has a resistance of 96 ohms, and it says find the EMF produced by the rod. Okay, so EMF, electromotive force. So get used to whenever you see EMF, you think voltage. Okay, EMF just means voltage, nothing fancy. It's the electromotive force that's produced by a magnetic field. We call it the EMF. Okay, so they want to know what the EMF is. Oh, well, that's pretty easy. Guess what? They gave me V, B, and L. I think I can do this. 5 times that is, this times that is 4 times 1.6 should be 6.4, yes, volts. Got it. So the EMF is equal to 5 meters per second times 0.8 Teslas. Now the hard thing, something that would be ornery to do, like on one of you guys' group exams, I'd like to see the cat fights that would take place on that, would be, all right, show why this is volts. Do the unit analysis of this. Show why it's volts. You'd have to go look up what Teslas is. I think we can do it. Remember what Teslas were? Teslas were what? I think Newton seconds. Are they Newton meters? Or and then Coulomb meter, like that, was what a Tesla was. So if we stick that in there, if we put that in there, then we've got velocity is meters per second. Oh, cool. And then we have then I've got Newton meters. I don't like that. I'm stuck over here with meters. Uh-oh. There I go again, doing physics on the fly. That may not be right for Teslas, but I'm almost positive that's right for Teslas. Let me look it up real quick. This is embarrassing. Newton second Coulomb meter. Yeah.
Meters do cancel, don't they?
Yeah, but not this extra meter over here. All of a sudden I've got a Newton meter. Uh-oh, ruh-roh, we've got a problem. I've got issues now. Oh, I'm still good. I'm golden. Because a volt is a Newton meter per Coulomb. Because what's a Newton per Coulomb? Remember what a Newton per Coulomb was? That's our measurement for what? The good old electric field, right? Right? And we also said that the electric field is volts per meter. Remember that? Probably not. Doing the unit analysis of E and M is very hard. And you've only been doing this for 4 weeks, so I've been doing it for 4 years, so I've got an advantage. Okay, so we got newtons per Coulomb, and which is electric field times meters, comes out to be volts. Okay, just trust me, it's volts. What would be the amperage through this thing? If we wound up that this is 6.4 volts, what would be the amperage? I. You can do this. You can do E, the electromotive force, equals IR. So you know R. So you can figure out I. It's just Ohm's law again, is all it is. And that comes out to be like 0.067 amps. This is a nice little problem because it covers everything. So we found the amperage. Let's find the power. Let's find the power. What is the power? Did they give us time? Oh, we don't need no stinking time. We can figure this out. Well, they do say for 60 seconds. Power. Power, watts. Power is what? Yeah, I squared R. I wasn't going for that one. I was going more for IV. Same thing. Or V squared over R. Any of them will work. But we've got all of them. Let's go ahead and change that V to this. And we could also do this. Any of those will work. Any of those will work. And so you come up with power is only 0.43 watts. And then the energy that is burned up, or that is used, or that is required, the energy would equal power times time. They told us the T was 60 seconds. I didn't tell you that. So you just take this 0.43 watts times 60 seconds, and you wind up with, you've only burned up 26 joules. Okay. All right. And that's the energy. And then they go through this big, the work needed to keep the light bulb burning. Well, guess what? 26 joules. I need to keep adding 26 joules of energy all the time, constantly, to keep that thing, per second, to keep that thing burning. All right. Good. Good, 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 good. Okay. I always screw this up every time, but I'm going to get it right this time. Because I practiced before I came up here. Okay, well, you already saw the demonstration. You already saw the demonstration with Lenz's law. But when I drop something down and it's in a conducting thing, there's a force that opposes the motion, basically. Okay? Because it creates an EMF that opposes the motion. So here we go. It's a good idea. Here we go. So I got this thing here. I'm going to try and draw this best I can. Got this conducting rod here. It's kind of embedded inside this thing. All right. I'm going to have a wire going through here with some resistance. Okay? And the magnetic field is coming out at us. Let's have B coming out at us. Okay? All right. So if B is coming at us, and this thing has a center of mass and has a weight, the force applied is equal to the weight. Here's the force applied. It's equal to the weight. Okay, so it's going down. Magnetic field's coming at us. The force is going down. So it's going down. Force is going. Sorry. Magnetic field's coming out. And the actual force is going down. So what's that going to do? That's going to create a EMF. In other words, the things have a velocity. Oh, there we go. Coming at you. Gosh, dang it. I did it again. This is about to make me angry. Okay. Oh, that's going to create a current that's going to go this way. It's going to create a current that's going to go this way, because what's going to happen, I'm right, I'm okay. Everything's fine. Don't panic. Here's the deal. Here's what happens. We're going to wind up, okay, we've got magnetic field going out this way, and we've got our particles that actually have a velocity that's going down. Okay, so that creates a force that's going this way, right? To the right. Are you with me so far? In other words, magnetic field's coming out at you. The charges that are on here are actually going down, so they've got a velocity that's going down. So what's happening is I've got a bunch of positive charges building up over here. And I've got a bunch of negative charges building up here. So I've created a battery with this thing. And so by convention, we have our current flowing like this. Okay? Actually, the current is going this way, but by convention, we have it going like that. So now I've got a new right-hand rule. I needed to do the one right-hand rule to get my charges all lined up. Now that I've got a current flowing this way, magnetic field going this way, which way is the force going on that wire? On the bar. It's going up. I screw that up every semester because I get ahead of myself. I forget. You have to establish it is okay that everything's collecting up over here and here. You have to establish first how the charges are getting collected up so that they create a voltage. All right, there we go. Okay, now, remember this guy? What was that? You remember him?
Flux.
Yes, the electric flux. Remember, we needed 15 gigawatts to accelerate Back to the Future? But anyway, with the flux, do you remember what it was?
E dot A.
Yeah, exactly.
E dot EA.
Yeah. EA. The electric field times the area. But guess what? Same thing here. I like the way Jared said E dot A because that gets us into the whole idea of it's a dot product thing. Okay? And it's a cosine. It's going to equal the magnetic field times the area that it's in. That's the electric flux. Okay? And it's measured in Webers or Webers. So Tesla meter squared is what is known as a Weber, a WB. Okay? Now, that's kind of important. Now, the key to the magnetic flux is this. Key to the magnetic flux is this. I'm trying to make this uniform in this area, this pi r squared area here. Okay? Now then, what did I draw there besides a bunch of geese flying? But that's actually what? The magnetic field going into the board, correct? Okay, so the magnetic field's going into the board. It is all perpendicular, okay? It's perpendicular to the normal. And so when they say cosine of phi, what they're talking about is the normal line. Okay? So the normal, it's all parallel to the normal. So the normal to this area, not to the magnetic field. The normal to the area is what? It's coming out at the board, or it's perpendicular to the board. Okay? All right, and the magnetic field is going completely parallel, right, to that. So what's the cosine of 0 degrees? 1. Okay? It's a little bit more, it's kind of confusing because we just got off of the force is equal to VB, QVB sine of the angle, or ILB sine of the angle. This one's cosine because they say measure it from the normal. Okay? All right? The normal to the surface area. And all of your problems will say the magnetic field is parallel to the normal. All right? If it says that, if it says magnetic field is parallel to the normal, then you know that phi equals 0, so cosine phi equals 1. So that's at a maximum. Your flux will be at a maximum then. Okay? That's kind of one of those, it's the geometry of the problem. Okay? So that's magnetic flux. Magnetic flux isn't too bad. But it's very important. It's used for something that's very important. And here we go. It's used in Faraday's law. This is one of the most important laws in electricity and magnetism today. It's because of Faraday's law that we have all this wonderful electricity and magnetism that we have today. Everything is 100 years behind when it was discovered and when they were playing with it, for the most part, in science. So when all those guys back in the 1910s, around that time, were discovering quantum mechanics and magnetic storage and all that kind of stuff, the way things happen at the really small scale, below the atom and things, that's what led to our cell phones today and things like that. Okay? They're more of a quantum mechanics type device than they are an electricity and magnetism device. They still need voltage to work, but and they still need the basics of E and M, but the properties are at the quantum level to enable us to have that much magnetic storage, to have that much data storage that we have. Like those little iPods, how many gigabytes do those little iPods have? 160 gig?
It's like
It's pretty thick though. Okay. Still. My first computer, my Packard Bell 386, had 85 megabytes of, that was it. That's all I could do. I couldn't even do the little Roger Rabbit video game that I got for it. You know, it was like, Who Framed Roger Rabbit video game. It would crash every time I'd try and play that. My daughter would get upset. Oh well. And it had 250 kilobytes of cache memory. If I put Word 2003 on that thing now, it'd take it 45 minutes to type a sentence. But anyway, now they've got it due to the magnetic fields that they can create at the very small. We've got iPods and, well, your little TI-83 and 84 calculators that some of you guys have is more powerful than the computers that launched us to the moon back in 1969. All right, anyway. All right, it's all due to quantum mechanics and Faraday and, gosh dang, semiconductors, which is an offshoot of quantum mechanics. All right, now here we go. So here's 22.4. So you've got the big idea. So far, let's review the bitting here, because I got off track there. We've got the electric motive force, which is equal to the velocity of the rod times the magnetic field times L. Okay? All right? It's equal to VBL. Okay? And the and it's an electric motive force, so it still keeps the same properties as voltage. It is voltage. Okay? So there you go. So it still has the same thing as volt. It is a volt. Okay, because it creates a positive and negative, so therefore it pushes charge, it pushes current, it creates current. All right, so now, here's the deal though. It's the changing flux. It's the flux changing over time also creates a current. And we get that straight from VBL, okay? Because if you look at V times L, what do you get? Let's break this down into its units. This is meters per second times meters, right? And so what's on top? Meters squared. That's an area. Meters squared. That's area per second. So here's the real equation to the whole thing. Is minus n, and it's negative by convention. Shows the polarity. Okay? It's negative by convention, so you just put your negative sign there, and then you do your algebra, and magic appears that you'll get the right where the positive and where the negative charges have collected. Okay? You'll get the right sign. Okay? And it is the change in the flux over the change in time. Now, all kinds of things can change. It's kind of like when I hammer the point home in Physics 1 about velocity having when it changes over time, that's an acceleration. The same thing when we saw uniform circular motion, the speed stayed the same, but what changed with the velocity? The direction. And so therefore it had an acceleration that went towards the center. Same thing here. Any of these guys changes. Either the magnetic field changing, and it can be changing direction too. It can be like an AC current. Remember when I was having trouble with my visual aids on Wednesday? Holding up the, okay, so if you, right hand rule number 2, your current, boom, we've got it. Okay, so now I've got a magnetic field going this way and a current wrapping around the coil like this, or I can go this way, have the current going, and now the magnetic field's going this way. But if I'm AC, what's happening to my current? Bump, 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 bump. So I'm changing that magnetic field all the time. Okay? And that creates induction. All right? That creates an induction also. So my magnetic field can be changing direction, or it can be changing. It can be changing. I can be changing the intensity of the magnetic field over time. Or I can be changing the area, or I can be changing the angle that it's sitting in. Okay? In other words, if I have, let's just take this situation here. Now what happens with this coil if I rotate it up like this? Then the magnetic field that's going through it is changing, right? Till we're like this. Then if I have the coil completely like this, how much magnetic field's going through there? None, right? So the magnetic field going through there, the area of the magnetic field would be decreasing as the angle's changing. So things going around in a circle can change the magnetic field, which creates a current in something else, which we will see. Okay? So all of those elements can be changing to create my voltage. All right? All of those elements can be changing to create my voltage. So let's take a look at the induced EMF by a changing magnetic field and the induced EMF in a rotating coil. So you get those two ideas. Then we'll go to Lenz's law, and then I'd better kind of stop because we've almost finished the chapter in one day, and that just doesn't seem right. Okay. By the way, you guys have already done all this because you did your lab with the RLC circuits. And they had a thing, they had this L thing, this inductor. You had no idea what it was, did you? Ha! Basically, it's a coil. It's a very tightly wrapped coil. Okay? So you had a resistor. So this is basically what you had, right? I'm going to just take a little lap here into chapter 23 just to show you what you were doing in your lab. Okay, you had a resistor and you had an inductor. You probably even had a drawing. And was it AC voltage that you all were using? Did they do the AC volt? Is this the drawing that was with your lab? Okay, well this is chapter 23, basically. Now what this inductor is, so this is how you got your RLC current. Inductor is measured in farads. Okay? An inductor is measured in farads, just after Faraday, Michael Faraday, and his compadre, his American counterpart, Joseph Henry, gave us the Henrys for the capacitor. Okay? All right? So they just give you what yeah, I forgot. We don't really derive the inductor here. They just tell you that it's in Henrys, right? Or due to self-induction. Basically, inductor, self-inductance is given in Henrys. I'm kind of getting into Wednesday's lecture here real quick. Just bear with for a minute. Okay. The self-inductance And this is basically what inductance equals, okay? It equals, L equals the number of turns in the coil, okay, times the magnetic flux divided by the amperage. Okay? So that's what your inductance is. Okay? And your coil, did they say anything about turns per meter or anything like that in your lab? They just gave you the inductance in henries for your thing? Or do you remember? Okay, whatever. But that's basically what. And remember, here's the main thing with any circuit. You're trying to control the amperage. Okay? And these things do something kind of cool. All right? In other words, if I put this kind of voltage in here, eventually what would happen was I'd get a bunch of positive charge built up here, right? Until no more could flow in. It would stop. Okay? And then if I took my battery out, then this would flow through here. But then it would build up in this inductor. That's what we're talking about here. It'd build up in that inductor, and then it would push it back the other way. And then I'd get a bunch of charge building up here. And then after it got built up so much, it'd push it back the other way. Okay, so you can get this, and some people think that, hey, if we can get this down to where it's a superconductor, we can get a perpetual motion type machine going. But what's happening is you're losing resistance, you're losing energy in the wire, you're losing energy in the resistor, and everything else. So, but that's what you all were doing. Okay, now, so let's get back to Faraday's law here. Faraday's law says this, basically this, that the EMF, and this is the biggie in the whole chapter, that the EMF is equal to minus n times the change in the magnetic flux divided by the change in time. Okay? Change in magnetic flux divided by the change in time. This is what, were any of you really cool when you were little and had the bike light that didn't require batteries? Had a little generator on the back tire? All right. You still have it? Okay. And even if, I mean, and you can even have it on your regular bike and stuff if you do a lot of biking and stuff like that. Basically what it does is creates a voltage by rotating that magnetic field. Okay? Rotating that magnetic field around a wire, so therefore it creates a current inside the wire and it lights your deal. So by the mechanical energy of the turning wheel, it creates that EMF, makes your battery. That's how it works. It's not magic. All right. So here we go. So let's take a look at the example, then we'll be done. All right. So this, a coil of wire consists of 20 turns or loops, so n equals 20. And each has an area of 1.5 times 10 to the negative 3. So the area is equal to 1.5 times 10 to the negative 3 meters squared. Okay, that's not bad. And a magnetic field is perpendicular to the surface of each loop at all times. Okay, so it says a magnetic field is perpendicular to the surface of the loop at all times. So that means when this loop turns, the magnetic field, it's not turning away from the magnetic field like when I was showing you down here. The magnetic field's always going to be perpendicular to it. Okay? So that means B's not going to change. To the surface, each loop at all times. And theta equals 0 at time t equals 0. The magnitude of the field at the location of the coil is B naught. Okay. So, theta final equals theta initial, which is going to equal 0. degrees. Okay? So our change in the cosine is going to stay the same. All right? And what we're going to wind up with here is, but B naught is equal to 0.005 Teslas, and B final is equal to 0.06 Teslas. Okay? What's the voltage? That's what they want us to find out. Find the average EMF induced in the coil during this time. Okay. And delta T equals 0.1 seconds. All right. Well, I think we've got everything we need. So we'll do this. We do the EMF then. The voltage is going to equal minus N minus 20. I don't put the 20 inside the print. And then I'm going to do the change in B. So that's final minus initial. So I wind up with, this is confusing. That looks like a flux. That wasn't. That's supposed to be the angle. In other words, magnetic field is always perpendicular to it. So that's fine. And then we've got B final, which is 0.06 Teslas, times the area, which is 1.5 times 10 to the negative 3 meters squared, minus, and this, oh, sorry, I'm going to have to do this. Minus 0.05 Teslas times 1.5 times 10 to the negative 3 meters squared over 0.1 seconds. There we go. That's my change in flux or my change in time. And when I get that, this should come out to be negative. Okay? This should come out to be negative, and it does. It comes out to be negative 3.0 times 10 to the negative 3 volts. Now, what happens to it when it goes back? What kind of voltage is it going to create? Positive or negative? It'll be positive. Because what's going to happen, now, go back. Now when we go back, what happens is this. Now I've got 0.05 minus this guy, so I get negative times a negative, which makes it a positive. So it'll be 0.0 times 10 to the negative 3 volts. Okay? All right, so now let's take a flat coil of wire. Has a area of, now we're going to do one, let's rotate the coil. This one we change the field. This one we change the field. And this one, now we're going to change the rotation. We're going to rotate. Change the EMF. Oh, gosh, one of those days. It must be Monday after a 3-day holiday. Okay. There. Change the EMF by rotation. So here's what this problem looks like. It says, okay, I've got an area of 0.02 meters. Area equals 0.02 meters squared. Okay. N equals 50. The magnetic field. The magnetic field is 0.18 Teslas. That's when it's that's when this coil is flat. Okay? Now when I rotate that coil through this angle of 30 degrees, my change in phi, not my change in flux, but my change in the angle. I'm going to go ahead and put angle here. is going to be from 0 to 30 degrees. Okay? So that's what's going to change over, I hope they give me a time, over 0.1 seconds also. Okay? So, let's take a look at this. So now what we're going to be doing is changing the angle. Okay? So we're going to be changing the angle. So I'm going to wind up with this. I'm going to wind up with the EMF is going to equal negative N times delta, the flux divided by delta T. Now that's a little confusing. This is the angle, remember. Okay. Now the only thing that's changing here is the angle. So I can pull everything out of this guy and do this. Go minus N times B times A, because the magnetic field's never changing and A is not changing. The only thing that's changing is cosine of 30 minus cosine of 0. So cosine of 30, is that the one that's pi over 6? That's what the cosine of 30 is? The pi over 6? Okay. So, here we go. So we've got minus 50 times 0.18 times 0.02 times pi over 6 minus 1. Is that positive or negative? Negative. I'm going to make this 6 over 6. Because that's my cosine of 0. So pi is less than 6. So I've got pi over 6 times 6. So I can probably do this out of the calculator almost. 50 times 0.18? No, I can't. I'm lying. I am so lying. Times 3.14 minus 6 over 6. Doesn't really matter. There we go. And when you get that done, see, this is going to be a negative times a negative, so it's positive, like 0.24 volts or something like that. Yeah, 0.24 volts. I can almost do that, because this would be 0.03. I don't even want to try. Okay. So there you go. Now, last thing, and this will make your head hurt, but it'll be okay, because next thing is Lenz law. I'm going to write it down. Oh yeah, because we got to take a little quiz. All right. Quiz will be over Lenz law, so pay attention here real quick. All right, now, here's what we do. Here's what Lenz law says. Okay, if I have a current, does that induce a magnetic field? Does a current flowing through a wire have a magnetic field around it? So if I have a, so here's the deal. If I have a changing magnetic field, okay, that's going to produce a current that will produce a magnetic field, okay, that will oppose the motion of the thing that was moving through the magnetic field to begin, the first magnetic field to begin with. So here's what this says. Here's Lenz law, and it's a tongue twister. Lenz law says this. I may not be able to put it up here because I forgot my glasses. That's all right. My arms are long enough. It says the induced EMF resulting from a changing
I gotta get used to
saying magnetic flux instead of magnetic field. I simplify it too much. It's a magnetic flux. Because we saw the magnetic field wasn't changing here, but the flux was. Changing magnetic flux, which could be a changing magnetic field, changing angle, changing area over time, has a polarity, okay? In other words, leads to a piling up of my positive and negative charges so that it creates a current. This is the piling up of positive and negative charges. So that it makes a battery. In other words, the polarity creates a battery, basically, is saying the same thing, that leads to an induced current. To an induced current whose direction is such, are you ready for this part? Whose direction is such that the induced magnetic field okay, so in other words, this current is making a magnetic field opposes the original flux change. That's what I was trying to say there at the end when I kind of ran out of words. Opposes the original flux change. Oh boy. What the heck are we talking about here? Picture's worth 1,000 words on this. Okay? And we'll kind of walk through the quiz. I'm going to give you the problem that I always assign will be the quiz over this part. I think you'll get it. I think you'll get it. So here we go. This isn't the quiz yet. Let's just take a look at what's going on here. All right, uniform magnetic field going into the board. Uniform magnetic field going into the board. I have a coil of wire out here. Got a coil of wire out here. It's falling. It's going to come, well, or I've got a string on it. I'm going to pull it through here. Okay? Now, right now, does it have any current going through it? Is it hooked to anything? No. Has no current. I equals 0. Okay, now, it starts to come inside here, and it's moving through here. Okay? Now, what's happening to the BA, the magnetic flux, cosine of 0 because it's parallel to the normal. Okay? What's happening to the BA as it's moving through here? Is it increasing or decreasing? The magnetic flux that it's experiencing. Increasing? Is the flux increasing or decreasing? It's increasing. Okay? So at this juncture, as it's falling this way, BA increasing. So guess what? Since BA is increasing, it's going to produce a current that opposes, thus the current will oppose BA increasing. All right? And the way I do this in my head is I go, okay, I know it's the area that's changing, but because the area is changing, I'm going to change the magnetic field. In other words, this guy with the magnetic field is going into the board, okay, and a thing coming down. We've got current. We've got a thing kind of going this, or we've got charge building up over here. All right? What we want is a current going through this wire, right-hand rule number 2, that opposes that magnetic field. Okay? So I want so which way do I want my magnetic field to go? Out. I want the magnetic field that's coming out. Okay? So if I'm going to have the magnetic field that's coming out, I want a current that's going this way. Okay? Whew. Now, it gets completely inside here. Now it's completely inside here and moving along. Is the magnetic flux in there changing at all? So what's happened to my current? It goes to 0. Because there's no changing magnetic flux. A's not changing. The magnetic field staying uniform. So the current is equal to 0. Now, it's starting to pop out. What's happening to BA here? It's decreasing. BA is decreasing. In other words, this is the magnetic flux that's creating the current. Okay? This is the magnetic flux that's creating the current, and it's decreasing. And so so this ring is going, oh, you're running out of juice. I need to help you. This one, you're gaining juice. I need to oppose you. This one, you're losing energy. So I want to help you out here to keep energy conserved. So which way is the current going here? Now I've got to have the magnetic field going into the board. So you cup your hand, right hand rule number 2, going into the board. So which way is your thumb pointing? The current is now going this way. Okay. Now, to hammer this point home, let's do this problem together. We're basically going to take the quiz together here. All right? Because if you can get your head around that, you've pretty much aced the course. That's tricky stuff. Let's take a look at, but I usually assign one of these problems just to be annoying. All right. Let's take a look at problem 30. Here's problem 30. I'm going to draw it over here. Oh yeah, we got a little time. Here's problem 30. It looks like this. Okay, here's quadrant 1, good old algebraic quadrants 1, 2, 3, and 4. Okay, and I have this funny looking little circuit thing here. Okay, now I'm going to draw my magnetic field. Uniform magnetic field comes all the way down through here like this. Okay, uniform magnetic field. All right. Now then, what we want to do is, at different junctures, when this thing, we want to know which way is the current going when it's situated like here. We want to know which way the current's going when it's situated here, like this. And I should probably, for clarity's sake, keep my magnetic field drawn in. And we want to know when it's situated like this. It's coming back to its original position. When it's over here. Which way is the current going? Okay. I think. Is that what they say? Oh, no. That'd be silly. You know that one. There's no magnetic field when it's like this. All right, this is your quiz. So I have this on a separate sheet of paper, and we'll work through it. We'll work through the first one together. All right? And then you all can work together. And so your answer is either going to be clockwise or counterclockwise. Okay? If your current is going counterclockwise, if your current is going counterclockwise, that means the magnetic field that it's producing is coming out. If it's going clockwise, if your current is going clockwise like this, that means the magnetic field it's producing is going in. Okay? Which way is our magnetic field here when we're starting going? Into the board. Okay? All right. So let's do the first one. So we're starting here. Now, this thing is rotating through here, and it's at this position. And it's continuing to rotate. Here's the question. BA increasing or decreasing? What's BA doing here?
Increasing.
It's increasing. The area underneath the magnetic field under this wire is increasing. So since it's increasing, which way do I want the magnetic field going that's opposing this guy? Right. I want the magnetic field to come out of the board. So which way is that? Is that clockwise or counterclockwise? Yes. That's counterclockwise, because if I'm going like this, because the current should be going like this. You can really see it with this guy. You got your current going that way, curl your fingers around, he's coming out of the board here. That's counterclockwise. Okay? CCW. What about in situation B? Yeah, it's 0. Yay, team. Why is it 0 here? Well, yeah, the magnetic field inside there never changes. The area, I mean, because basically what we're talking about is when he's here, even, once he gets to here and is falling through like that, then his area, the BA in here never changes. So therefore, since BA is not changing over time, there's no induced current. It's 0. Okay. Now, he's swinging. He's coming out of here. So which way should the current be going? Clockwise, because we want to help it this time. We want to go in. So if we, yeah. We saw Brittany going through the gymnastics. Right. If we want to go in, then that way, going on this bar here, if we want to go in, then that means the current's going this way, which is clockwise. Wasn't much of a quiz, but do you see how that works? Yeah? Maybe, sort of, kind of, possibly. Okay. Or are we just going, well, July 31st is coming up and I don't have to worry about this shit ever. Let's not drop the packs just yet. You're working too hard. We've still got a ways to go. Don't we still have like 4 weeks left? Isn't this like the first day of the second half? We just had the opening kickoff. Okay. It's all right.